Hi, I'm going to review some of the strategies for solving systems of linear equations. Remember, a system of equations is a collection of two or more equations, each containing one or more variables. In this video, I'll solve linear systems in two variables. I'll review how to solve systems by graphing, and I'll review how to solve systems by using the substitution method and by using the elimination method. Let's start with this system. 2x plus y equals 3 and y equals x minus 3. Remember, for this equation, there are an infinite number of solutions. That means an infinite number of ordered pairs that would make this equation true. Similarly, this equation has an infinite number of solutions. And when we're solving a system, we're trying to find all of the solutions that they have in common. Well, we're going to look at the picture of the solutions for each of those equations. That means we're looking at their graphs. So I'm going to write some directions here, and they'll be solve by graphing. Let's start with the first equation. We have 2x plus y equals 3. Let's solve for y. So we have y equals negative 2x plus 3. So we recognize that the slope is negative 2 and the y-intercept is 3, since it is in slope-intercept form. So now let's come over to our grid and graph this one. So we'll go up to the y-intercept of 3, and we'll use the slope to find other points. So that's down 2 over 1, down 2 over 1. We'll find one more, down 2 over 1. And we could put a straight edge down and draw the line. Now for our second equation, we have y equals x minus 3. So for this one, the slope is equal to 1 and the y-intercept is negative 3. So let's graph this one as well. The y-intercept down here at negative 3, the slope is 1, so up 1 over 1, up 1 over 1, up 1 over 1. And now again, we can draw the line. So this line represents all of the solutions to the first equation, and this line represents all of the solutions to the second equation, and we see right here they share this point. And notice that that point is 2, negative 1. So our solution to the system is 2, negative 1. And you can substitute that ordered pair into the system and confirm that you have it right. Let me show you. So we have 2 times 2 plus negative 1 equals 3. That's 4 minus 1 equals 3. That's true. And we substitute it into the second equation, and we have negative 1 equals 2 minus 3. That's negative 1 equals negative 1. That's true as well. So we have confidence that we did it correctly. Let's do another problem. This one we will also solve by graphing. The equations are y equals 1/2 x minus 5 and x minus 2y equals 2. Let's start with the first equation. It's y equals 1/2 x minus 5. It is in slope-intercept form, so we can identify the slope as a half, and the y-intercept is at 0, negative 5. So let's plot that on our grid. Down here is our y-intercept. And our slope is 1/2. That means up 1 over 2, up 1 over 2. And you could find as many points as you needed. That's probably enough. So let me draw the line. Our second equation is x minus 2y equals 2. We could graph that by using the x and y-intercept, but I can also solve for y and put it in slope-intercept form, so let's do that. So if we subtract x, we have negative 2y equals the opposite of x plus 2. Divide by negative 2, and you have y equals 1/2 x minus 1. So our slope is 1/2, and our y-intercept is negative 1. And maybe you recognize what's about to happen because they each had a slope of 1/2. Let's draw our second line here. The y-intercept is -1. The slope is 1/2, so up 1 over 2, up 1 over 2, and we'll draw the line. And we can see that the lines are parallel, which is what we knew would happen as soon as we saw that their slopes were equal. But since we're looking to see what points they share, we see that they don't share any points. They have no solution in common. So we would say for this problem that there is no solution. We would say that this is an inconsistent system. I'll write that down too. Let's solve one more system by graphing. It will be y equals 1/3 x plus 1 and x minus 3y equals -3. Let's start with our first equation again. We have y equals 1/3 x plus 1, and I have a slope of 1/3 and a y-intercept of 1. Let's plot that on our graph. So our y-intercept is here. Our slope is 1/3. So up 1 over 1, 2, 3. Up 1 over 1, 2, 3, and I can draw my line. My second equation is x minus 3y equals -3, and I could certainly solve for y as I did on the previous example, but we could also just find the x and y intercepts. If I set x equal to 0, I would find the y-intercept. And if we did that, we would have -3y equals -3, and we would find that y equals 1. And to find our x-intercept, we set y equal to 0, and we would have x equals -3. And let's look at what that would look like. Our y-intercept, same as our previous equation, and our y-intercept is -3. And you notice we have, in fact, the exact same line. In fact, if I had solved for y, it would have looked like this. -3y equals the opposite of x minus 3. Divide by -3, and you would have had 1/3 x plus 1. And you would have noticed we have the same equation twice. So the equations were completely equivalent. So what's the solution? Well, the solution to this system is the set of all points on this line. In fact, we could say there are infinitely many solutions. And there are a variety of ways to answer this, but I'm going to just stick with this for now. Infinitely many solutions. We would also say this kind of a system is a dependent system. The last three examples represent the three possibilities that can happen when you're solving a system of linear equations in two variables. You can have two intersecting lines, in which case you will be able to name an ordered pair that is the solution, like -15, 22, or you'll have a pair of parallel lines, in which case you'll have no solution, and we say that the system is inconsistent. Or you could have two equations that are equivalent and hence have the same graph, one line, and then the other line is exactly the same line, in which case you would have infinitely many solutions, because every point on the line is a solution, and we would say that that is a dependent system. Let's turn now to solving a system by using the substitution method. So here's our system, 5x plus 2y equals 1, and x minus 3y equals 7. We could graph it, look for their point of intersection, and that would be our solution. but I want to do it differently. Again, we're going to use the substitution method. That requires that we solve for either x or y in one of the equations. So I could solve for this x, this y, this x, or this y. And I usually choose whatever feels easiest to me. As soon as I see the coefficient of this x is a 1, I'm going to choose to solve for this x right here. So in equation 2, we have x minus 3y equals 7. If I solve for x, I would have x equals 3y plus 7. Now here's where the substitution happens. This is equation 2, and we're going to substitute this expression that represents x into the x in equation 1. So here's equation 1 with the x removed, and I put in parentheses. And now I can fill in the parentheses with what is equal to x in this problem, and that is 3y plus 7. So let's write that 3y plus 7. And now I have a linear equation to solve. So we have 15y plus 35 plus 2y equals 1. So we have 17y plus 35 equals 1. Subtract 35 from both sides and divide by 17. So our y value for the ordered pair that is a solution to this system is -2. Now I can substitute that -2 into this equation right here. I can substitute it in right here, or I can even come down here and substitute the 2 in right here. I'm trying to find the x value that goes with that y value. So let's substitute it in right here. So my equation would become x equals 3 times -2 plus 7. And I just have a little arithmetic to do here. And I have x equals 1. So the solution to this system is 1, -2. And as with the first example I gave, when we were solving by graphing, you could substitute 1, -2 into both equations and confirm you have the correct solution. Let's solve another one. Here it is. 8x minus y equals -67, and 2x plus 3y equals -33. So again, the directions are use substitution to solve the system. So I solve for whatever variable seems like it's easiest to isolate. So I'm going to choose this y right here because the coefficient is just a -1. But it really is a matter of personal preference. You could solve for this x if you prefer, or this x, or this y. So I'm going to solve for y in the first equation. So we have 8x minus y equals -67. I'm going to subtract 8x and divide or multiply by -1. So the y value for this problem is equal to 8x plus 67. This comes from equation 1. I do need to make sure this time I substitute then into equation 2. Make sure you substitute it into the other equation. So I have 2x plus 3 times 8x plus 67 equals -33. And now we just have a linear equation to solve, and I have 2x plus 24x plus, 201 equals -33. So that's 26x plus 201 equals -33. Subtract 201 from both sides, and we have -234 on the right-hand side. And let's divide by 26. So we have x equals -9. As with the previous example on the left, once we have one value, we can just back substitute, and find the other value. So I have x, I'm trying to find y. So I'm going to substitute this -9 right in here. I could come back to the first equation up here and substitute it in here or here. It's a matter of personal preference. I'm substituting it in right there. So we have y equals 8 times -9 plus 67. So we have y equals -72 plus 67, and that gives us y equals -5. So the solution to this system is -9, -5, and this problem is complete as well. We're going to solve two more systems using the substitution method. Let's start with this problem on the left. You'll notice this first equation has already been solved for y. So let's just make the substitution. So I'm substituting 1/3 x plus 2 into the second equation. It's kind of nice when one of the variables is already isolated. So here we go. We have x minus 3 times 1/3 x plus 2 equals 11. So I substituted the expression that equals y from the first equation into our second equation. Let's distribute our -3. So we have x minus 6 equals 11. Well, when we subtract x minus x, we get -6 equals 11. And we know that is never true. That means there is no solution to this particular system. And if we were to look at the graphs of the equations in this system, we would see that they are parallel. But we didn't have to graph them to determine that. Again, the variables were eliminated, and we had an untrue statement. That's why we know there's no solution. Let's look at the system on the right-hand side. It's very similar. I already have the y isolated in the first equation. Again, I'm going to substitute it into the second equation. So I have x minus 3 times 1/3 x plus 2 equals -6. Again, I distribute, so I have x minus 6 equals -6. I simplify on the left-hand side, and I have -6 equals -6. Well, this is different from the problem on the left-hand side. On the left-hand side, this equation is never true. -6 equals -6 is always true. And that means we have a scenario where these graphs would be the exact same line. Every point that is a solution to the first equation is also a solution to the second equation because they're equivalent equations. So we would write infinitely many solutions. And we know this is a dependent system. So I just wanted you to see those two special cases that occur that you can determine that they've happened even if you don't graph them. Let's move on to our elimination method. Let's solve this system first using the elimination method. And by the way, sometimes the elimination method is called the addition method. You hear both fairly frequently. But let's get started. What the elimination method allows us to do is, in a system, add everything on the left-hand side together and set it equal to everything on the right-hand side added together. Because after all, if this 5x minus 2y is equal to 1, and this -3x plus 2y is equal to 13, then the sum of everything on the left should equal the sum of everything on the right. So let's do it. I'm going to add everything on the left-hand side together, and I will get 5x minus 2y minus 3x plus 2y. That is a 2x because the -2y and the positive 2y are eliminated. And on the right-hand side, I get a 14. So when I divide by 2, I have x equals 7, and we're halfway done that quickly. We still need the y coordinate that goes with that x coordinate for the solution, but as with the substitution method, we can just use back substitution to figure out the y value that goes with it. So let's do that substitution. I'm going to choose the first equation. Didn't really matter. 5 times 7 minus 2y equals 1. And solve that equation. 35 minus 2y equals 1. So negative 2y equals negative 34, or y equals 17. So the solution to this system is 7, 17. And it's complete. Let's look at this next one. We have x minus 11y equals 16, and 3x plus 4y equals 11. Notice if we were to add the two equations together as they are right now, we would get 4x minus 7y equals 27, and that is not helpful. Look at the problem on the left-hand side. What made it be nice? The negative 2y and the positive 2y were eliminated when we added it together. The coefficients of the y's were exact opposites. That's what you need to happen when you're using the elimination method. So let me erase and let's start again. I'm going to use the fact that this coefficient is 1 to help me in forcing the coefficients to be exact opposites. We need the coefficients of x or the coefficients of y to be exact opposites. So if I could make the coefficient of this x become a negative 3, it'd be the exact opposite of this positive 3. So I'm going to multiply equation 1 by negative 3. And of course, that's our multiplication of property of equality that says that you can multiply an equation by any number you want to, as long as you don't multiply by 0 and wipe out the equation. So my system will become negative 3x plus 33y equals negative 48. And I'm going to leave the second equation unchanged. 3x plus 4y equals 11. Now when I add the two equations together, I get 37y equals negative 37. Divide by 37 and I get negative 1. Let's now find the x coordinate that goes with it. Substitute negative 1 into either of the equations, right here or right here. I think I like the first equation best. So let's do the substitution. We have x minus 11 times negative 1 equals 16. So that's x plus 11 equals 16, and we get x equals 5. So the solution to this system is 5, negative 1. Let's look at this problem. It says to use the substitution or elimination method to solve. If I were going to use the substitution method, remember I would solve for x or y in one of the equations, and I noticed that none of them have a coefficient that's 1, although mathematically that doesn't matter at all. As a practical matter, I would probably then choose to go to the elimination method. In using the elimination method, then, I need to force either the coefficients of x or the coefficients of y to be exact opposites. So that's going to require multiplying both equations by a number. Let's see. I noticed that the x's already have opposite signs, so I'm just going to choose to force these to be exact opposites. This is a 5, but if I multiply it by 6, I could make it a positive 30. And if I multiply this by 5, I could make it a negative 30. So that's what I'm going to do. Multiply equation 1 by 6 and multiply equation 2 by 5. And I will have a system that is completely equivalent. Multiplying equation 1 by 6, I get 30x plus 18y equals 6. And multiplying equation 2 by 5, I get negative 30x plus 20y equals 15. When I add the equations together, I'll have 38y equals 21. And I divide by 38, and I get a lovely 21/38 for the y value. Now I need the x coordinate that goes with that y, and I could certainly substitute this value into either equation and solve for x. But I don't want to do that. I want to give you another option. We already have the y coordinate for our solution. We need the x coordinate of the solution. We have the option of going back to the original system, which is 5x plus 3y equals 1, and negative 6x plus 4y equals 3. And instead of eliminating the x's, let's eliminate the y's. So we'll do that by multiplying the first equation by 4 and the second equation by negative 3. Do you see why I chose those numbers? That will force the coefficient of y to be 12 in the first equation and the coefficient of y in the second equation to become negative 12. So we'll now be eliminating the y's. So our system becomes 20x plus 12y equals 4 and positive 18x minus 12y equals negative 9. When we add the equations together, we get 38x equals negative 5, or x equals negative 5/38. So we have those two coordinates, negative 5/38 and 21/38, and we put them together, and we have the solution to this system. Let's solve one last system. This is 3 times the quantity of x plus 2y equals 2x plus 5y minus 11. And the second equation is x over 5 plus y over 2 equals 2. And it says we can use substitution or elimination to solve this system. Well, I have no idea when it looks like this what strategy would be best. And I don't have to live with this equations looking like this. I would take a step or two to make the system look nicer. Then I'll make a decision about what strategy to use. So for equation 1, let's just start by distributing. So we'll have 3x plus 6y equals 2x plus 5y minus 11. And equation 2, I don't particularly like with the fractions, so let's multiply by 10. Not because I'm using elimination, but because I want to clear out the fractions and write an equivalent equation so I don't have to manage those fractions anymore. That's my preference. So I would get 2x plus 5y equals 20. Oh, I like that a lot better. Now, the first equation I don't really like very well the way it looks, so let's subtract 2x and subtract 5y, so we'll get the variables on one side, and then I will take another look at the system. So when I do that, when I subtract 2x, I would just have 1x, plus, I'm subtracting 5y, that means I just have 1y equals negative 11. And I have 2x plus 5y equals 20. And notice that this one would be very nice for either the elimination method or the substitution method. I think I'll use substitution just because the last few examples I did were using elimination. So let's use substitution. I have both the x and the y in the first equation with a coefficient of 1, so it would be pretty straightforward to solve for either of those. I'm going to solve for y in equation 1, and that means I have y equals the opposite of x minus 11. I substitute that into equation 2 for y, and I have 2x plus 5 times the opposite of x minus 11 equals 20. Make sure you pay attention to which equation you had and which equation it needs to be substituted into. This was a variation of equation 1, so I needed to make sure I substituted it into equation 2. Let's continue. So we have 2x minus 5x minus 55 equals 20. Or negative 3x minus 55 equals 20. Add 55. And we have negative 3x equals 75, and divide by negative 3. And I have x equals negative 25. Let's make a substitution back into an equation to find the y value that goes with it. I do not have to substitute it into the original system. You can substitute this into any version of any equation. So I would choose to substitute this x right in here. Could have been here. Either place would have been nice. The x plus y equals negative 11, or the y equals the opposite of 11 minus, or the opposite of x minus 11. So let's substitute it in. Y equals the opposite of negative 25 minus 11. So I have 25 minus 11, or 14. So the solution to this system is negative 25, 14. And it's complete. I hope you'll practice solving some systems by graphing, substitution, or elimination.